Have you ever thought about what nothing is? And what is emptiness? Imagine a universe devoid of all matter and any form of radiation. But that's not all. Think about true nothingness. It's not just empty, it lacks space, time, and even atoms. Yet suddenly, in a single moment, everything appeared in absolute emptiness. How is that possible? This is perhaps the most fundamental question in all of science and philosophy. Everything we know about our universe today is based on mechanics, processes, and causality. We strive to understand these processes and reasons for why we see things as they are. But at a fundamental level, we don't yet know how or why the universe came into existence and why there are things in it that defy all the laws of physics and our understanding of creation. Perhaps, as the famous cosmologist Stephen Hawking once suggested, there was truly nothing before this. Considering space and time as inseparable, intertwined properties of the universe we live in, the birth of the universe marked the beginning of time. Because without the beginning of time, there could be no space and therefore no universe. But what if there was no beginning, and there's only a limit to our observability? Today, many scientists believe that there was a period of rapid expansion in a fraction of a second, known as inflation, which heralded the Big Bang and set the stage for everything that followed. But some physicists argue that this wasn't the only inflationary period in the universe. According to their views, inflation continues somewhere else, eternally giving rise to new universes. Or perhaps our universe is just the last in a long, potentially infinite series of expanding and contracting cosmoses, a theory known as the Big Bounce. In this theory proposed by physicist Paul Steinhardt, it's all about the infinite expansion and contraction of the universe. The Big Bang, the universe expands, then at some point it stops. Starts contracting, and time runs backward, and after the contraction, another Big Bang occurs. Or maybe our understanding of the scale of what's happening is fundamentally wrong. Some physicists believe that our universe came into existence as a momentary collision of dimensions. This is the so-called string theory, attempting to explain the fundamentals of reality as tiny, vibrating strings in an 11-dimensional hyperspace, where the 3 dimensions of space and 1 dimension of time that we perceive are just one thread in the grand tapestry. And the birth and growth of our universe occur when threads of a higher order collide. Or perhaps there is something else that escapes our understanding of the laws of physics. At this moment, the history of the origin of our universe remains a mystery, an adventure with multiple choices. But one thing is for sure, 13.8 billion years ago, something truly happened. What do you think is the hottest place in the universe? Many might say it's in the core of our star, the Sun. For thousands of years in human history, the Sun was considered a god. To the ancient Egyptians, it was Ra, sailing through the sky in his regal boat. To the ancient Greeks, it was Helios, driving his chariot across the celestial sphere every day. But neither the ancient Egyptians nor the Greeks could even fathom that the temperature at the core of our star reaches 15 million degrees Celsius. And for the universe, that's not the limit. For instance, during a supernova explosion, in the dramatic death of a star, the superheated outer shell is ejected in all directions for many light years, leaving a neutron star at the center. The temperature of this star reaches 100 million degrees Celsius. But that's not the highest temperature you can find in space. Temperature is nothing more than a manifestation of particle energy, their motion and speed. Absolute zero, marking 0 on the Kelvin scale, equivalent to minus 275.15 degrees Celsius, represents the lowest limit where particles should theoretically come to a halt if it were possible to reach. But there's also an upper limit, absolute hot, marking the highest temperature before particles are torn apart by their own energy. This temperature is more than 1 4/10 quintillion degrees Celsius, but is better known as the Planck temperature at 1.4 multiplied by 10 to the power of 32 Kelvin. Such extremely low and high temperatures are beyond our understanding. We are evolutionarily tuned to numbers that relate to us, which might make these temperatures seem too vast to have any practical application on Earth. However, in the vast scale of the cosmos, these temperatures are very much real. Everything in our universe is controlled and defined by 4 fundamental forces of nature, such as the strong and weak nuclear forces, electromagnetism, and gravity. Gravity keeps you seated in a chair, and it becomes more noticeable when you fall off the chair. It also holds Earth's atmosphere and the Earth itself in orbit around a star, providing the climate conditions necessary for life. Nevertheless, despite this, gravity is relatively weak, and you can overcome it with the muscles of one arm. For example, to grab the remote control and turn on the TV. The images on the TV come to life thanks to millions of tiny pixels emitting visible light, which is another form of electromagnetic radiation that travels through the room and enters your eyes. Your eyeballs themselves are evolutionary marvels, but ultimately, they depend on the properties and behaviors of atoms within electrons and nuclei, held together by the electromagnetic force. Atomic nuclei themselves are held together by the strong nuclear force, where protons and neutrons come together at the center of an atom. Every atom in your body, in the TV, in everything you see, and even in the air you breathe depends on this force. When your eyes focus and interact with moving images on the TV, each of the neurons in your brain fires about 200 times per second. This entire balanced electrical potential relies on the right balance of potassium in your body. Potassium, like other elements, is held together by the strong nuclear force, but there's more to it, because potassium is weakly radioactive. About 5,000 potassium atoms decay every second, and this decay is due to the weak nuclear force. At a distance of 150 million kilometers, the core of our sun burns with the heat of a stellar furnace, synthesizing hydrogen into helium. This incredibly powerful reaction is responsible for the warmth that sustains life on Earth. And all of this also depends on the weak nuclear force, which may be weak in name but mighty in its capabilities. Each of these four fundamental forces, gravity, electromagnetism, strong and weak nuclear forces, acts together to shape our perception of the universe. However, in the very early moments of time, the conditions for establishing the rules and physical components were quite different during the era of the grand unification that followed the Planck epoch. There are only two forces, electroweak interaction and gravity. Characteristics such as mass, weight, scent, and color, for instance, did not exist. This is what scientists encounter when they study the behavior of fundamental forces at higher energies. The energies present in the nascent universe. If you sharply raise the temperature, the individual properties of the weak nuclear force and electromagnetic interaction start to weaken and merge with each other, as indeed occurred during the grand unification era. By July 2022, the famous space telescope James Webb had settled into its designated orbit at Lagrange Point 2, about 1.5 million kilometers from Earth. After a month-long journey and nearly a year-long deployment and calibration phase, it was finally ready to commence its scientific work. But when it gazed into the deepest corners of the observable universe with its 18 golden mirrors, scientists were shocked upon seeing the images from the revolutionary telescope. Astronomer Allison Kirkpatrick of the University of Kansas, who studies the evolution of galaxies, wrote in the scientific journal Nature that at 3 a.m. she couldn't sleep, wondering if everything she had ever done was wrong. For a month, these images and Kirkpatrick's comments took on a life of their own. The fixed speed of light means that the deeper we peer into space, the further back in time we look. At a distance of just 200 million years from the birth of the universe, the James Webb Space Telescope saw galaxies. What's more, these galaxies turned out to be much more structured than astronomers had expected. The theories of star and galaxy formation couldn't explain this, and that's what troubled Kirkpatrick. Soon, her concerns were extrapolated to challenge the Big Bang theory, and some media outlets claimed that the telescope had disproven this historical theory with its very first images. However, Kirkpatrick was only concerned with existing galaxy formation theories, not the creation of the entire cosmos. The inexplicable structure of early galaxies meant that there was a part missing in our understanding, not just what we knew. The complete explanation of how the universe came into being is that it was under a much more serious threat for far longer than we can imagine. When we look at the large-scale structure of the universe as it is today, we find phenomena that don't entirely match up. First, there's the average temperature. Despite the temperatures of stars being several million degrees Celsius, the temperature of empty space is just a few degrees above absolute zero. The average temperature we observe in one direction is surprisingly similar to any other. This temperature is only 2.7 Kelvin, or minus 272 degrees Celsius, and it's the same everywhere in the universe. But how can this be? If the universe gradually expanded over almost 14 billion years, how do 2 points more than 14 billion light-years apart average out without exceeding the speed of light? The fact that we observe such thermal uniformity now means that thermal uniformity existed in the earliest times of the universe. This fact seems incredibly unlikely, given the nature of quantum fluctuations in the early cosmos. In Einstein's general theory of relativity, It stated that massive objects create curves in spacetime that govern the evolution of matter in this space. Stars, galaxies, and black holes leave traces in the form of indentations in the spacetime structure. However, as we approach a large object, these indentations smooth out, creating a more even structure that resembles the average temperature of space. Wherever you look, you see balance, geometry, whether in your body or in animal bodies. Scientists have noticed that evolution explicitly favors these balanced, symmetrical forms, not least because they can be built from much simpler instructions than other more complex and non-repeating geometries. It's the mathematical and algorithmic simplicity that underlies the symmetries found everywhere. In science, symmetry has a much broader meaning than its everyday use. It means that everything remains the same, no matter what, from the laws of physics to the conservation of energy and momentum in the universe, which, by its nature, is symmetric. For instance, positive charges balance negative ones. Some particles rotate clockwise, others counterclockwise. And if you measure the force of gravity on Alpha Centauri, you get the same result as in our solar system. However, the universe is not perfectly symmetric. In the apparent perfect equilibrium of space, there are also imperfections. There's a matter-antimatter imbalance, and many of these imbalances are key to understanding the functioning of reality. But in the very beginning, it was different. Cosmologists believed that in the first second, everything was completely symmetric. There was a balance, but everything changed with the separation of forces and the emergence of something that had a significant impact on the existence of mass. At the moment when the four fundamental forces completely split and crystallized as separate entities, a new era was born. This is the era of quarks, defined by the interaction of matter. One of the largest stars in the universe is Ice-Cutie, with a diameter 1,700 times that of our Sun. It, like all stars, is made up of the smallest elements found in the universe, such as hydrogen and helium atoms. Hydrogen and helium, despite their simplicity, represent the building blocks of protons, neutrons, and electrons. But these are not the smallest elementary particles. Protons and neutrons are made up of even smaller particles called quarks, whose properties, along with the properties of electrons, ultimately determine the characteristics and behaviors of everything, including the largest objects in the universe. In 1973, a young physicist, Edward Tryon, was attending a lecture by Dennis Sciama, considered one of the fathers of modern cosmology. During the lecture, there was a brief pause, and suddenly Tryon exclaimed, "Maybe the universe is just a vacuum fluctuation." There was subdued laughter in the audience. However, by December 1973, Tryon published a paper titled "Is the Universe a Vacuum Fluctuation?" In this paper, Tryon attempted to explore the peculiar consequences of quantum vacuum, leading him to ask another question: what is the total energy content of the universe? It was clear that all the mass and motion must represent a tremendous amount of energy, but there's also potential energy in gravitational and other fields, and this potential energy is negative. Tryon attempted to sum up all the energy in the universe, and it turned out that it balanced out, with the total mass being zero. Tryon realized that a zero fluctuation could last forever. Now we know that in our quantum universe, something could arise from nothing. But what could happen inside true nothingness, beyond time and space, still remains a question beyond the reach of science. So, for now, all we can do is be patient and await new discoveries, including those from the James Webb Space Telescope. And that's it for today. Leave your comments, give a like if you enjoyed this video, and stay tuned for more exciting cosmic encounters.